function is a relation where each input maps to only one output. We say a function is strictly increasing if it only goes up from left to right. It's strictly decreasing if it only goes down from left to right. The word monotone in math means you've got a function where it's either strictly increasing or strictly decreasing. It's one or the other. It doesn't do both. And then lastly, a one-to-one function is a function where each output is mapped to by only one input. That makes it one-to-one. So a one-to-one function is a more specific, more restrictive kind of function. Let me talk a little bit abstractly about what I mean here. So if I have a situation like this, is this a function? No, this is not a function. Why? Yeah, because exactly. There's an input value, 1, that maps to 2 different output values. And so this is not a function. Okay. Let me draw you a new picture. Oh, I don't like that. Ellipse. Let me try again. Let's now try something like this. Is this a function? Yes. This is a function. Is this a one-to-one function? No. So the issue here is just that the 4 has 2 input values that map to 1 output. It's actually fine. You know, if 5 doesn't have anything mapping to it, that's okay. And we know this is a function because every one of the inputs maps to only 1 output value. I don't have a situation like before where 1 input maps to 2 outputs. So this is a function. It's just not one-to-one because this 4 has 2 different input values that map to the same output value. So we say it's not one-to-one. Okay, a real one-to-one function might look like something like this. A one-to-one function is, of course, a situation where each input maps to 1 output. That makes it a function. And what's special is that every output value has only 1 input value that maps to it. So this is a one-to-one function. Okay, so the function x squared is not one-to-one. You know, in terms of my inputs and outputs. 0 maps to 0 in x squared. Where does negative 3 map to? Positive 9. Where does positive 3 map to? 9. Oh, that also maps to 9. So this is why it's not a one-to-one function. Okay, so that's what we're worried about. This time we're worried about whether or not a function is one-to-one. Turns out a function is one-to-one. Oh, and I should have fixed my notes. This should say continuous. There we go. So a continuous function is one-to-one if and only if your continuous function is monotone. So you remember monotone means it's either strictly increasing or strictly decreasing. The reason why that is because if I had a function, draw one real quick, that is not monotone, something like this, then I could always choose one output value or one y value. And this time it corresponds to multiple x values, right? In this case, 3 different x values. If 3 different input values map to one output value, then it's not one-to-one. And if you think really carefully about this, monotone means it's either strictly increasing or strictly decreasing. This orange function is not monotone because it's increasing, then decreasing, then increasing again. The reason I'm able to reach the same y value more than once is because I reach it the first time by increasing. If I were to keep increasing, there's no way I can come back to it. But if I switch and then I start decreasing again, well, then I can go back and reach the same y value. And then if I switch again and I start increasing again, then look, I can reach the y value a third time. But if I don't allow myself to ever switch, if I say, I'm either going to stick to increasing or I'm going to stick to just decreasing, right, like something like this, well, then there's no way I can go back and attain the same y value again. So this leads to something called the horizontal line test. Earlier, maybe last week we talked about the vertical line test. The vertical line test was a way to determine whether or not a relation was a function. But this time a horizontal line test is going to tell you, okay, I've got a function, but is it one-to-one or not? If you can think of any horizontal line that crosses through your function more than once, it's not one-to-one, because a horizontal line only has one specific y value. So if the horizontal line passes through your function more than once, that means there's one value that is mapped to by multiple x values. But if you can't find a horizontal line that passes through more than once, that must mean the function is monotone, and that must mean it's a one-to-one function. So, one question I'm going to ask you on Wednesday, in your test, is please determine whether or not each of these functions is one-to-one. And I'm not actually going to give you the formula. I'm giving myself the formula so that I can put this into Desmos. But I won't actually give you the formula on the test, so please don't look at the formula for a minute. Just look at the picture. Here's my function. Here's my horizontal line. Is this function one-to-one? Yeah, because it only passes through one time. Okay. Is this function one-to-one? No, because I can find a place where the horizontal line passes through more than once. All right. Is this a one-to-one function? No, because again, more than once. What else do I have? Is that a one-to-one function? Yes. Any horizontal line only passes through this function one time. It's not one-to-one. What about this one? No, it's not one-to-one. Cool. Okay, a function has an inverse function. That's the new word in this definition. A function has an inverse function if and only if it's one-to-one. An inverse function is the function that inverts the mapping from input to output. So I'll try to draw a little picture again. And this time, let's say my function is f of x equals x cubed. The x cubed function would map -2 to -8. The x cubed function would map 0 to 0, and it would map +2 to +8. Okay. Well, what about the function cube root of x? That would map -8 to -2. That would map 0 to 0, and that would map 8 to 2. That's what I mean when I say the inverse function inverts the mapping from input to output. Another way you can say the same thing is you might say the domain of f is the range of its inverse. And likewise, the range of f is the domain of the inverse. So if you can't tell, we're going to use a tiny little superscript -1 to represent the inverse function notation. If I call my function g of x, then the corresponding inverse would be g inverse of x, where the little -1 means inverse. And maybe I didn't say this, but I know that x cubed is a one-to-one function because it's strictly increasing. And if it's strictly increasing, it's monotone, and that means it's one-to-one. And that's how I know it has an inverse function. And this inverse function is given by the x cubed function. Inverse functions also come in pairs. So if I say my function f is x cubed, and the inverse of that is the cube root of x, I could have said this. I could have said my function name is g, and g of x is equal to the cube root of x. Then g inverse would be x cubed. Yeah. So it's a mutual relationship. It goes both ways, right? Just like I could say, my brother is Jeff, and then if you ask Jeff, he would say, my brother is Drew, and it goes both ways. So inverse functions come in pairs. All right. If you compose a pair of inverse functions, like if I say f composed with f inverse of x, then whenever I write them out composed and I simplify as much as possible, I just get plain old x back, right? To use my previous example, this would be the cube root of x cubed, but that would just be x. And then likewise, this next one, if I were to take f inverse of f of x, this would be the cube root of x cubed, which is x. Okay, so how do we determine in general whether two functions are a pair of inverse functions? Well, you could compose them, simplify as much as possible, and then ask yourself, is this x? So real quick, if I want to determine if these functions f and g are inverse functions, let's compose. Let's say f of g of x. Well, that would be the cube root of x minus 5 cubed plus 5. So are those inverses? Yes. They are inverse functions because when I composed them and I simplified, I just got x. It doesn't matter the order. You could do g of f of x, and you should still get x once you finally finish all the simplifying. Okay, determine whether these functions are inverse functions using composition. Let's mix it up this time and do g of f of x. And so my g function is 5x over x plus 2. And so I'm plugging in f of x into the argument now, so it's 5f of x over f of x plus 2. The f of x function is 2x over x minus 5. Okay, if I do 5 times all of this, I could just multiply the 5 in the numerator and get 10x over x minus 5. In the denominator, if I want to add 2 plus all of this, I would have to find a common denominator. Of course, that common denominator would just be x minus 5, and then I would get 2x plus 2x minus 10, so 4x minus 10. Dividing is the same thing as multiplying by the reciprocal. And so the x minus 5's cancel, and I get 10x over 4x minus 10. If I wanted to take out a 2, I could get 5x over 2x minus 5. But what I ended up with here, after I simplified as much as I could, is just the expanded form of a rational function. So it's fully simplified. There's nothing more you can do to simplify it. And it's still not x. So that means these functions are not inverse functions. Okay, we checked it, we composed them, we simplified, and it was not x, and so these are not inverse. Any questions about that? All right. That's if I give you a pair of functions and I ask you, are they inverse to each other? But if I only give you one function, how would you find that function's inverse function? Well, it's easy. You swap x and y. Every x becomes a y, every y becomes an x, and then you just rearrange the equation to solve explicitly for y. So, if I give you the function y equals 2x minus 1, we swap and we make every y into an x and every x into a y, and then I want to solve for y. So, let's add 1 to both sides. And then let's divide both sides by 2. That's it. So this is my inverse function of the one I was given. Let's do it again. We're going to look at this function, y equals 2/3 minus 1 over x. And then we're going to swap x and y. So every y becomes an x, and every x becomes a y. And now we try to solve explicitly for y. I'm going to subtract 2/3 from both sides. And then I'm going to go ahead and multiply both sides times y. And then I'm going to divide both sides by x minus 2/3. That's it. That's your inverse. Is that easy? Very good. This is probably the trickiest one we're going to do today. At least in my opinion. And we've got the function f of x equals 2x plus 3 over 5x minus 1. I just rewrote it with a y instead of an f of x because the next step I want to do is I want to replace all of the y's with an x. And I want to replace all of the x's with a y. And then we're going to try to solve for y. I'm going to start off by multiplying both sides by the denominators, right? Just like solving a rational equation. We don't like to have denominators in our equation, so we try to get rid of that. Multiply both sides by the denominator. And then on the left side of the equation, let's expand it by distributing the x. Now, I want to collect all of the terms that have a y on the left side of the equation, and all of the terms that don't have a y, I want to put those on the right side of the equation. So 5xy gets to stay on the left, and I also want to move 2y over to the left side of the equation, so I subtract 2y from both sides. I want to move the x over to the right side, because that term doesn't have y. So I add x to both sides, and then I add 3. Or yeah, the plus 3 stays there. Okay. Next step, I want to factor out the y on the left side. So I get y times 5x minus 2. And then lastly, to solve explicitly for y, perfect. Now, to zoom out and see, my function's name was f. So for my answer choice, I'm actually going to write this fancy inverse notation. And this is the way your answer choice is going to appear on your test. Since we just found the inverse of f, we'll call it f inverse of x equals x plus 3 over 5x minus 2. Okay, so that took us like 6 steps, right? That's the longest, most difficult one you're going to see today. Was there any questions about any step in the algebra there? Sure. All right. More examples, because it always helps to see more and more. If I've got the function f of x equals 2x minus 3 cubed, we write it like this, and then I swap, make the x into a y, I make the y into an x. How do I solve for y? Yeah, I should take the cube root of both sides. And then, add 3 to both sides, and then divide by 2. The way I'm going to write my answer choice is like this. Because I'm dividing by 2, and I'm using the fancy inverse notation to say I just found the inverse of that f function. Okay, I think there's one more. And here we have the function y equals the 5th root of 4x plus 5. The y becomes an x, and the x becomes a y. And now I want to solve for y. I raise both sides to the power 5. And then I subtract 5 from both sides. And then I divide by 4. So I'm going to write my answer. F inverse of x is going to be 1/4 x to the 5th minus 5/4. All right, super easy. If I have an odd power of x, like I have x raised to the power 2023, this is a one-to-one function. But if I have x raised to the power 2024, yeah. Odd powers of x are one-to-one. Even powers of x are not one-to-one. This is important because that means any odd power of x is going to have an inverse function, right? The way that x cubed has an inverse function, the cube root of x, or x to the 5th has an inverse function, the 5th root of x, and so on. All of the odd powers are one-to-one because they're all strictly increasing. But if I have x squared, not strictly increasing, so these don't have inverse functions because they're not strictly increasing. That's the idea. You remember the degree of a polynomial. And the degree of a polynomial written in expanded form is just the largest power of x that you see. The same definition applies to rational functions. If you have a rational function and it's written in expanded form, then the largest power of x you see anywhere in your rational function, whether it's the numerator or denominator, that's the degree of your rational function. That means a degree 1 rational function would have to look like this, right? A degree 1 rational function is at most a degree 1 polynomial divided by a degree 1 polynomial. And so it's going to have to look like f of x equals ax plus b, that's a linear polynomial, divided by cx plus d, which is another linear polynomial. And here's a little formula. It's a formula that is completely optional to you. I'm not going to force you to memorize this. It's up to you whether you want to pay attention for the next 1 minute or so. But if you choose to memorize this formula, it's a really good shortcut. The only thing you have to remember is say the a and the d, they switch places, and they become negative. But the b and the c remain the same. Now, if you can manage to remember that, this is the reason it's such a great shortcut. Because the longest, most difficult problem we worked today in lecture was this one, right? We had to swap the x and the y, we had to multiply by the denominator, we had to expand the left side, we had to rearrange the terms so that we collected all the y terms on the left side, we had to factor out a y, and then we had to divide. This is the problem that I see most missed on the test I'm about to give on Wednesday, right? It's a long problem. There's like 6 steps. What if, instead of working the problem, I just said, hey, that's a degree 1 rational function, so I know to write the inverse function, I just have to switch the place of the a coefficient and the d coefficient, change their plus or minus sign, and leave the b and the c the same. Well, then I can just write down the answer, right? Just look at it. And look, it matches what we got before. So, yeah, it cuts down on your longest type of problems, and you probably make fewer mistakes. If you can, like I said, I know you have to memorize the formula. You got to say, I'm going to switch the a and the d and make it negative, but if you can remember that, then it makes things easier. The proof of this is not hard at all. To write the proof, you just say, I'm going to find the inverse of this function with the a, b, c, and d all still set in there in their abstract form, and I'm going to replace the y with an x. I'm going to replace the x with a y. And we do all of the same steps we did before. So multiply by the denominator. Distribute the x on the left side of the equation. Collect the terms that do have a y on the left side and the terms that don't on the right side. Factor out the y on the left side and then divide both sides by the remainder, which is cx minus a. And then, of course, you replace that y with the fancy inverse notation, and that's how you can see that the negative d and the negative a are swapped, but the b and the c remain the same. And that's your formula. So you don't need to know the proof. Right? You just have to know, hey, this is a little shortcut I can use. Right here. What would be the inverse of this function? Yep. You just swap the a and the d, make them both negative. You can see it to remain the same. Here a is 3, b is negative 4, c is 7, and d is 1. Okay, this one is a little bit tricky, but it still technically meets the format ax plus b over cx plus d. Okay. A is 0. B is. C is. Yeah, negative 3. And then D is 2. So if I want to write the inverse function, I write negative 3x minus 0, right, for the minus a at the end, but who cares about minus 0? That's the answer. And, if I wanted to, I could multiply the top and bottom by like negative 1, right? And I could say that is the answer following 2. So, you're aware of that. Okay, new topic. If I graph together on the same xy plane, if I graph a function and its inverse function, then these two functions are going to be a mirror image of each other across the line y equals x. And the line y equals x is a line that passes through the origin because the y-intercept is 0. And it has a slope of positive 1, so it's going up at a 45-degree angle through the origin. Let's see what that looks like. Is that it? No, I got my minus signs mixed up. So, let's see what that line is. It would be something like this. All right, in red, you've got the function 2x minus 1. In blue, you've got its inverse. This is what I mean. The red curve is a mirror image of the blue curve across the line y equals x. Do you see it? Okay. So a question that I'm going to ask you on Wednesday, and I'm not going to even tell you what the formulas are, right? Pretend you don't see these formulas. I'm going to give you functions and then ask you if they are a pair of inverse functions just based on looking at a graph. So again, pretend you don't see this. Pretend you don't see this because I know by looking at the formula you could tell, but I want you to look at the picture. Is the blue curve and the red curve, do those represent a pair of inverse functions? Yeah. The blue curve is a mirror image of the red curve across that green dashed line. Right? Is this blue curve and this red curve a pair of inverse functions? No. It's a mirror inverse, the blue curve is a mirror image of the red curve across the y-axis, sure, but that's not the question. Inverse functions are a mirror image of each other across the line y equals x. And that's not the case. So these are not inverse functions. Let's do another one. Oop. Really? I think that's it. Okay. Are those inverse functions? Yes. Those are inverse functions. They're a mirror image across this line. And are these inverse functions? No. No, the red curve is not a mirror image of the blue curve. right across that green line. There's no way. And then one more. Are these inverse functions? No. In fact, there's a big glaring problem here, which is the blue function is not one-to-one. The blue function fails my horizontal line test. Now, if I were dealing with the inverse of the blue function, what would that have to look like? Well, it would look like swapping the x and the y, right? It might look like that. If I wanted to create a mirror image of the blue curve across the y-axis. What's the big issue with the green curve now? Yeah, the green curve fails the vertical line test. So the green curve represents a relation, but it's not a function. Green curve's not a function. And that's why we say, you know, if your curve fails the horizontal line test, it can't have an inverse function, because making a mirror image of that would involve a curve that fails the vertical line test, and that's not a function. So you can't have an inverse function if you fail the horizontal line test. So back to this story, because this is not a perfect mirror image, red and blue, but what if I just kind of do this? Right? That does look like an inverse function in terms of mirror image over here. I just have to ignore the left side of the plane and it works. So this is kind of inconvenient to have this whole part over here. So what I could do is I could restrict the domain of my blue function and say, okay, I know I could have negative values in my domain, but I'm going to intentionally restrict the domain to only include x greater than or equal to 0. And I'm doing this so that the blue curve and the red curve represent inverse functions. Very nice. So some functions are not one-to-one, but we can make them one-to-one using domain restrictions. We might ask, if I've got the function f of x equals square root of x, what is the inverse function of f? X squared. Okay, the problem is x squared is not one-to-one. It goes decreasing and then increasing. So what kind of domain restriction do I need to include in order to make this really the inverse function? Yeah. If I restrict the domain to only x greater than or equal to 0, then that works. Then it's strictly increasing as long as I force x greater than or equal to 0. And so here's what this looks like. The red curve is now square root of x, and the blue curve is now x squared, right? That's what x squared looks like, but I don't want this left branch. That's messing up my symmetry, so I say, now let's force x to be greater than or equal to 0. And now the blue curve is strictly increasing, so it's one-to-one, and it does have an inverse function. Okay, here's where things get just a little bit tricky. If my function is negative square root of x, what's the inverse function? Okay, let's swap and make y equal to x and x equal to y. I take the negative of both sides. I square both sides. So the inverse function is parentheses negative x squared. But that's the same thing as positive x squared, isn't it? Two negatives make positive. So the inverse function of negative square root of x is x squared. Of course, this is not one-to-one, so I need a domain restriction. What's the domain restriction this time for? Yeah, Brianna's right. So this is going to be x less than or equal to 0. So think about this for a second. At the beginning of class, I said the domain of your original function is the range of your inverse function. And the range of your original function becomes the domain of your inverse function. What would be the range of my g function? Well, the range is all the negative numbers and 0, right? Because this minus sign out front forces everything to be the negative numbers, but also the square root of 0, 0. So that means the domain of its inverse has to be the range of the original function. And so that's why I'm restricting the domain of the inverse to be all of the negative numbers and 0. Okay? We swap the domain and range whenever we create an inverse function. So now we've got this example which says g of x is equal to negative square root of x plus 1. The inverse function is, well, let's go ahead and show every step of our work. I don't want to miss out on anything here. Don't want to make any silly mistakes. So I change the y into an x, and I change the x into a y. And then I subtract 1 from both sides. And then I would also want to take the negative of both sides and then also square both sides. Okay. This is clearly a quadratic function because of the squared part. This is a parabola, so it's increasing and decreasing. It's not one-to-one. I know I need a domain restriction. What should be the domain restriction here? I'll give you a hint. The domain of the inverse is the range of the original function. What's the range of the original purple g function? Yeah. Everything on the number line between negative infinity and positive 1. Because I've got the plus 1 on the end, but everything else has to be negative that I add to it. So the range of my original function, which is the domain of my inverse function, is x less than or equal to 1. I'm using little curly brackets for the domain restrictions. That's how Desmos likes it. But let's do that real quick. So this is the function in red, negative square root of x plus 1. And we said, okay, after finding the inverse, the analytic way where we swap the x's and the y's, and we rearrange and solve for y. I got y equals negative x plus 1 squared, but we knew that this was not 1-to-1 because it's squared. It was going to be a parabola, blah, blah, blah. And then we said, well, I must restrict the domain of my inverse to be the range of my original function. And we said the range of the original function was x less than or equal to 1. And now you can see that blue curve and that red curve, they're a mirror image of each other across the line y equals x. Ta-da. Okay. Now I've got a domain restricted function and I want to know what's the inverse. So here is my function x minus 3 raised to the 4th power. And we say the domain restriction, because this is an even power, so it's got to be restricted in order to make this work, is this. So the inverse function maybe I'll explicitly show you every step in the process here. Let me say y equals x minus 3 to the 4th power. And then I write, okay, y is now x is now y, and then I solve for y. So I mentioned this before, but the square root principle extends to all even numbered roots. So my inverse function should be plus or minus the 4th root of x plus 3. Whenever I write this down, though, I'm thinking to myself, the range of my inverse function should be the domain of my original function. My original function has the domain x greater than or equal to 3. So should I choose the positive or the negative 4th root? The positive one. I choose the positive 4th root of x because I want the range of my inverse to match the domain of my original function. Okay, one more, and then we're done for the day. Now I've got the function g of x is equal to x minus 5 squared. And I've got the domain restriction where x is less than or equal to 5. So g inverse of x, that's what I'm trying to find. Let's go ahead and write this out with x's and y's. We change the y into an x and the x into a y. And then I want to solve for y. So I take the square root of both sides, but the square root principle tells me I have to include a little plus or minus sign. And that gives me y equals plus or minus square root of x plus 5. The only question remaining is, I need to choose, do I want positive square root of x or negative square root of x? Negative. Why did you say negative? Yeah. I want the range of this inverse function to match the domain of my original function. The domain says x has to be less than or equal to 5, and so I have to make this negative to have the range match the domain.